So we're building up to this idea, this concept called the p-value. And in hypothesis testing, I talked last class about how one of the most confusing aspects of hypothesis testing was foremost this conclusion, the phrasing of the conclusion. So that's one of the most confusing things. And hopefully it's not as confusing since we've talked about it. But if it still is, let me know. But the second most confusing things for students who first learn this is this idea of the p-value. And one of the reasons it's so confusing is because the textbook presents it very poorly. It's very confusing reading the section on the p-value in the textbook. So it turns out this idea of the p-value is really not confusing at all. It's very straightforward. It just happens to be the textbook explains it poorly. But hopefully, after we talk about it in class, it'll be a lot more clear. Okay, so let's build up to this idea of the p-value. So as a review, the way that we determined in this example that the observations in the body of the distribution and not the tail, apart from just looking at the picture, is we compared z-score to z-score. So we compared this z-test versus z-critical. And as example, let's go ahead and do the example where the observation happened to be in the tail. So when we observed 124 successes in our sample of 1,000, and we knew the observation was in the tail of the distribution, let's go ahead and do that example. So we're going to compare these two values, z-test versus z-critical. So z-test comes from a formula. So let's go ahead and plug in the numbers in the formula again. So the numbers are going to be x, which is 124, and then n is still 1,000, p is still 0.7, and then the denominator is the same. So go ahead and plug this in and let us know what we get. Okay, good. So negative 39. So not only is it on the left, but it's very far to the left. It's negative 39 standard deviations away from the mean. Negative 9.35. 0.75. The rest of you guys getting that? I was expecting a very negative number, but I don't know if I was expecting it that negative. Okay, because this is so negative, this might not be very illustrative, as illustrative as I would like. So let's use 524. So we know it's still going to be less than the mean. So let's go ahead and try 524.
Negative 12.15.
Yikes. Let's use 624.
Negative 5.24.
Okay. How about 664?
Negative 2.48.
Okay, like that. Okay, 664. Okay, what that's saying is that you have this idea that 70% or more of all internet users have used your site, but it turns out in your sample that only 664 out of 1,000. So that's still less than the mean. But the question is, can you go ahead and reject your idea? Is it far enough away from the 700 that you would expect for you to say that the idea is false? So it turns out that when you evaluate this, you'll see that it's 2 points, what now?
2.4, negative 2.4.
Negative 2.4,
Yeah.
negative 2.48. So the z-score is negative 2.48. So that's over here, that'll have this 664 here. We'll have a z-score of negative 2.48. Okay, so the question is it low enough to be considered in the tail of this distribution? Where there's some boundary here where the tail starts, where the left area is only 5%. Okay, good, so we looked that up, z critical ended up being negative 1.645. That means everything to the left of that is in the left tail. So we're definitely to the left of that. So this, this data point is definitely in the left tail. So because this data point is in the left tail, we can compare these two numbers. Z-test is negative 2.48, and z-critical is negative 1.645. And because this z-critical is defining where the left tail starts, and everything to the left is in the left tail, we're to the left, so we're in the left tail. So we can conclude that this is in the tail. And because the observation is in the tail of the distribution, then therefore we reject HO except H1. But I'll just state it in terms of HO for now. So just reject HO. So again, this is a summary of basically what we have done, which is we compared two z-scores, z-test, which came from our observation, z-critical, which is where the tail starts based on the confidence level, and because it's in the tail, then we reject HO. So we reached that conclusion by comparing z-score to z-score. But you know that there's a z-score table that has a relationship between z-score and area to the left. Or z-score, the area to the left is just a convention. The table very well could have been constructed as an area to the right. We just happen to use the convention of left area. So we have a relationship between z-score and area. And so because we have that relationship, there's a one-to-one relationship, and because of that, instead of comparing z-score to z-score, we can compare area to area instead. So, in other words, instead of comparing these two boundaries, here, this red boundary to this blue boundary, we can compare now area to area. So this red boundary has a left area associated with it, and really the left area is this tail. So we compare the area to the left of this critical z-score. So I'm gonna write this as area to the left of z critical. And we're gonna, because that area is already the tail area that we know, we're gonna compare left area to left area. So this is z-test that we found before, now we're gonna find the left area of that. So now, instead of comparing z-score to z-score, we're comparing left area to left area. Yeah.
It's 0.006.
Okay, just give me a moment. So the only difference between this line and the previous line is instead of comparing z-score to z-score, now we're comparing the area to the left of one z-score to the area to the left of the other z-score. And the red quantity here, the area to the left of z critical in the picture, this total left area, what does that end up being? Yeah, that's the 5%. So, just to make that clear here. So that's the total 5% here. So that's the area to the left of Z critical. Now, if you look just at the picture, the area to the left of Z test, because we know Z test is inside the tail, that area is going to be this area here. So just by looking at the picture, is the area to the left of Z test, this blue area here, is it going to be less than or greater than the area to the left of Z critical, which is the red area? Less than, because it's only a subset of it, a small part of it. So this area to the left of Z test will be smaller than the area to the left of Z critical, which was the 5%. And so we know that we should expect it to be smaller, but let's go ahead and calculate it. So how do we calculate the area to the left of Z test? Yeah, find it in the chart. So go ahead and look up negative 2.48. 0.0066. So just like what we expect from looking at the picture, this area in blue that represents the area to the left of our observation, Z test, is indeed less than the total red area of 5%. So if you compare these two numbers, this blue number is definitely less. And so because it's less, that means that that area, it needs to be contained within the other area. So that means the observation must be inside the tail. So because this left area of our observation is less than the left area of Z critical, which denotes the tail, that means the observation must be on the tail. So just by comparing these two numbers now, we can conclude that the observation is in the tail. And again, we make the same conclusion that we reject HM. So we reach that conclusion instead of comparing two Z-scores like we did before, now we're comparing area to area. Any questions? And in particular, the area that we're choosing, so note that if you have an observation here, that technically it has a left area and it has a right area. In this case, you notice that we happen to pick the left area. And the reason we picked the left area is that we can have corresponding areas in the same direction. And so because the area to the left of Z critical, that's the one that represented the tail. So because this represented that tail area, it involved finding a left area, so the other area we choose analogously the same direction. So we're comparing left area to left area. So let me start summarizing. So this area here that we just found, the 0.05, that's really the tail area, and that's really alpha. Because the confidence level was given at 95%. So alpha is always the complement of that. Alpha is always 1 minus the confidence level, or alpha is 5% in this case. So this area to the left of Z critical that we picked, Z critical is where the tail starts. The area to the left of that is that 5%, or alpha. So when we're making this conclusion, we're comparing this area in blue here, which is the 0.0066, to 0.05, which is really alpha. So we're comparing this number to alpha here to make the conclusion about whether the observation is in the body or the tail. So the number that you use to compare to alpha is called the p-value. So let's start summarizing what we just did. So this is calculating the p-value. So the first step to calculate the p-value is look at your observation in this case, the observation, had a test z-score. So relative to the test statistic, I'll just say relative to the observation. And I'll say i.e. z-test. We want to find the area in the same direction as the nearest tail. So in this example, we had an observation or z-test that was negative 2.48. So relative to that observation with a z-score of negative 2.48, we wanted to find the area in the same direction as the nearest tail. So in our case, did we have a one-tail test or a two-tail test?
One.
You know, one-tail test, not only was it a one-tail, it was a left tail. So we had a left tail, and our z-score, in this example, happened to be in that left tail. So in the first step, to finding the p-value here, we want to find the area in the same direction as the nearest tail. So our observation here is technically going to have a right area, and it has a left area. But we want the area in the same direction as the nearest tail. So in this case, the nearest tail is the left tail. So therefore we want, relative to our observation, we want the area to the left of that observation, because the nearest tail is on the left. If it had been a two-tail test and the observation had been over here, then we have two tails, but the nearest tail is still on the left side. So always, to find the p-value, the first step, we want to find the area in the same direction as the nearest tail, relative to our observation. So here, that's why we ended up finding a left area, not a right area. So that was the first step to finding the p-value. And that's why we ended up finding this area that was to the left of this z-test of negative 2.48, and that's how we got this number. That's the first step of finding the p-value. The second step is to multiply that area that you just found by 2. Or not by 2, by the number of tails. So multiply that area by 2, or by the number of tails. So in this example, that area that we just found should be multiplied by what?
1.
By 1, because we only have a one-tail hypothesis test. And it turns out that that number that we just found multiplied by 1 doesn't change the number. So any number multiplied by 1 doesn't change. So in this example, then this step ends up not doing anything. But we need to consider this step in the general case. Any questions? All right, so let's go ahead and practice. Let's say that you have a left tail hypothesis test, or a right tail hypothesis test, and let's say that the observation is on the left of that, and it has a z-score of negative 1.3. So based on what we just talked about, go ahead and find the p-value.
I'm just gonna confidence level
Yeah, it turns out that it doesn't matter what the confidence level is, when you're calculating the p-value. In the next step, when you're interpreting the p-value, that's when it comes into play. But for now, it doesn't matter what the confidence level is, whether it's 95 or 99. The p-value is based on just these steps that we just talked about. So go ahead and calculate the p-value based on these steps. Yeah.
The p-value is 0.9032, right?
Yeah, very good. So let's talk about it. So let's go through the steps. So this is relative to the observation or z-test. That's here. So relative to here, you're gonna have either a right area or a left area, but we want the area in the same direction as the nearest tail. So is the nearest tail a right tail or a left tail here? Nearest tail is a right tail, so we want the area to the right of this observation. So we're gonna find this right area. So it'll be this total area in blue. So if you look that up, look up a z-score of negative 1.3, table will give you a left area, but we want the right area. So we're gonna subtract from 1 from the number that we see in the table. So that ends up being 0.9. What?
0.0968.
Yeah, that's the left area, and then we're gonna subtract from 1 to get the right area. What is it?
9032.
0.9032. Okay, so that'll be this total right area. So that'll be the p-value. So that's in this example. Any questions? So p-value here will be 0.9032. Let's say that I change the example around a little bit, where now I have a two-tail test instead. So let's say I have a two-tail test. My observation still has a tested z-score of negative 1.3. So go ahead and find the p-value.
It should be 0.1936,
Okay, how'd you get that?
because it's 2 times the z-test to the nearest critical, the nearest tail,
So,
right?
did you take the previous number and multiply by 2?
Yes.
Okay, so you need to make sure that,
Sorry, not the previous number, the original number
oh yeah, yeah.
of, to the left of negative 1.3.
Okay, very good, that's correct. Good, so let's go over that. So relative to the z-test, relative to this observation, again, it's gonna have either a left area or right area, but we want the area in the same direction as the nearest tail. So the nearest tail in this case will be a left tail or a right tail? It'll be a left, right? So now we want the area to the left of this z-score. So the area to the left will be from the table that we got before. Before we found the right area, now we want a left area. So this is gonna be 0.0968. So that's the answer for step 1 here. And then step 2 is to multiply that by the number of tails. But now that we have a two-tail test, now it differs. Where we're gonna take this number and multiply by 2. So the z-score now, or the p-value now will be 0.0968 times 2. Looks like 0.19 something.
1930.
Okay, so that'll be the p-value in this case. Any questions? Okay, so now that we calculate the p-value, let's talk about what we do with it. Let's talk about how to interpret the p-value. So this is calculating the p-value. And this will be interpreting the p-value. Remember, the whole meaning of the p-value is that it's the number that you use to compare directly to alpha to determine whether the observations in the body or the tail. So if you look at this picture, we know that Z critical is where the tail starts, and we're gonna have an area relative to Z critical, that'll be the tail, that'll be alpha. So again, if the observation happened to be inside the tail, then we're gonna get Z test here. Then the p-value, the way that we calculated it, was a function of the area in the same direction as that nearest tail. So this blue area here will, for example, be the p-value. So, so in this example, so remember the p-value is a function of the area that is in the same direction as the nearest tail. So in this case, this area in blue here, the p-value, is less than the area in red, which is alpha. So if p-value is less than, let's say less than or equal to alpha, then what can we say about the observation being inside or outside the tail? So the p-value, this area in blue, is less than alpha, the area in red. Is the observation in the tail or the body?
Tail.
Yeah, it's in the tail, because it's only a part of alpha. So that means that the observation's in the tail. And because the observation's in the tail, you reject HO. So once you've calculated the p-value, we now want to make a conclusion using the p-value of whether the observation's in the body or the tail, and we do that by comparing the p-value to a single number alpha. So we compare the p-value to alpha, and if the p-value is less than alpha, that means the observation's in the tail, and we reject HO. But if we have this case, where this tail has a value of alpha and the p-value is greater than the p-value because its overlapping area is greater. So if the p-value is greater than alpha, then is the observation in the body of the tail. Yeah, that means it's outside the tail area. This blue area is greater than the red one, so the observation has to be in the body of the distribution. And like we said before, the observations in the body of the distribution, we fail to reject HO, or do not reject HO. So when you have the p-value to interpret the correct conclusion, all you do is compare the p-value to alpha, and if the p-value is less than alpha, that means you reject HO. If it's greater than alpha, then do not reject HO. And so there's a cute saying to help you remember this, and the cute saying is, if the p-value is low, the null must go. So the saying's cute because it rhymes. All right. So if the p-value is low, Okay, so that's just a saying that summarizes what we just said. So if the p-value is low relative to alpha, then the null must go. You reject the null hypothesis. So if you go to the learning lab, they'll try to help you by giving you another cute saying, and they'll say if the p-value is high, the null must fly. That's a terrible saying. Because you notice this wording needs to be very specific. And when you say that the null must fly, what does that even mean? Does fly mean that you allow it to happen? Does fly mean that you don't reject it? It's just not at all clear what it means for the null to fly. So because of that, don't use that saying. So use the saying, if the p-value is low, the null must go. But if the p-value is not low, then the null must not go. So all you do is insert these not clauses in here, and it retains the correct meaning. So if the p-value is not low relative to alpha, then that means the null hypothesis must not go. So you do not reject the null hypothesis, just like we expected. Any questions? Okay, so let's make this concrete with an example. So let's say that you're reading a scientific paper. And let's say that the researchers publish their results and they publish their p-value. And let's say that the p-value they publish is 0.03. Let's say that you're reading the paper and you want to have a confidence level of 95%. So you want to be 95% confident in your conclusion. So the question is, what should your correct conclusion be in terms of the null hypothesis? Should you reject the null hypothesis, not reject the null hypothesis?
For the other one, do not reject HO, is that just fail to reject HO?
That's the same thing, yeah.
Okay, just double check.
Yeah.
Thank you.
Wouldn't you reject HL because 0.03 is less than 0.05, which is alpha?
Okay, excellent. So to use the p-value in interpreting the conclusion, remember we said that you just compare the p-value to a single number, which is alpha. And the way that you get the number from the confidence level is that it's the complement of the confidence level. So you just subtract from 100% or 1. So alpha then would be 100% minus 95%, which is 5%, or 0.05. So then to correctly interpret using the p-value, you just compare this p-value to alpha. So if the p-value is, now you use the cute saying, which is if the p-value is low, the null must go. So is the p-value low here relative to alpha? Yes, so the p-value is low, so therefore the null must go. So in this case, your conclusion would be to reject the null hypothesis. But that's the conclusion in terms of the null hypothesis. So remember, we always want to bring it back to the original claim. So what you would do then is go back and look at the paper and see whether the claim is the null hypothesis or the alternative hypothesis. And that would be step one of hypothesis testing. And then So in this case, you either reject HO or you accept H1, depending on whether the claim is HO or HO.
Just out of curiosity, would the paper literally say this is a null hypothesis?
No. You would have to go back and you'd have to identify the statement that contains equality, and that would be the null hypothesis. Okay, good. So let's say that this is the first situation where the p-value is 0.03 and the confidence level is 95%. Let's say that there is another reader who demands a higher confidence level, and let's say they demand a confidence level of 99%. So, what would the conclusion be in that case?
Fail to reject HO?
Okay, very good. So same process. We're going to compare this p-value to alpha based on the confidence level. So alpha will be 0.01. And alpha is always going to be 1 minus the confidence level regardless of the number of tails, whether it's a one-tail test or a two-tail test. So alpha is always going to be 0.01. And then now you're going to compare the p-value to alpha. So the p-value is 0.03 compared to alpha. So the p-value is not low relative to alpha. So if the p-value is not low, the norm must not go. So we do not reject HO. Any questions? Okay. So yeah. Okay. So this is an example to show that why the p-value is predominantly used. So it turns out when this was first presented, it seemed like the p-value was just an alternative to comparing z-scores. But it turns out that the p-value is now preferred to reaching a conclusion by comparing the two z-scores. And the reason for that is that different readers can easily have different confidence levels and easily be able to determine their correct conclusion based on that particular confidence level. So all they have to do is compare their p-value to their alpha, which is easily found by subtracting their confidence level from 100% always. So just compare p-value to alpha and you can easily reach the correct conclusion. And so that's why the p-value is now used as the de facto standard in research. So researchers will always publish their p-value. So if this idea of the p-value had not existed, then what else would the researchers have to present to you for you to be able to reach the correct conclusion? Instead of comparing p-value to alpha, what would you have to compare some measurement to another measurement to reach the same conclusion about whether the observations of the body or the tail?
Something like z-test to z-critical?
Very good. So if this idea of the p-value had not existed, then the researchers would have had to release their z-test to you, and you would have been able to reach the same conclusion if you had compared their z-test to the correct z-critical based on your confidence level. So now you would have to go and compare your z-test to z-critical. As opposed to comparing p-value to alpha. So it turns out that alpha is much easier to find because alpha just comes from 1 minus the confidence level always. But this z-critical is much more cumbersome because what would you need to do to find this z-critical? Yeah, you'd have to have a table in front of you, and not only that, you'd have to use your confidence level, but you'd have to know how many tails there were in the hypothesis test. Whether there's a one tail or a two tail makes a big difference as to what area that you use to look up in the table. So then you'd have to go back and study and see, is this a one tail test or is this a two tail test? Versus when you're comparing it directly to alpha, alpha is always 1 minus the confidence level regardless of the number of tails. And the issue of one tail or two tails was already baked into the p-value. So remember, when you calculated the p-value, this is the second step where you multiply by the number of tails. So the researchers handled that for you in determining the number of tails when they calculated the p-value. So all you have to do when you interpret the p-value is compare that p-value to alpha, and then you're done. So this idea of the p-value is much more convenient in trying to reach a conclusion than comparing z-score to z-score, even though you will get the same result. Any questions?